Now, I hope you can see what I'm sharing.
Yes, very well.
Yes, yes, okay. So we want to continue with what we were doing last time. We had looked at RSA, and that is what we are continuing with. So today we are to look at how to attack RSA. Now, so we don't learn how to attack so that we can be attacking other people's communication. The essence is that so that we can know how to make our work and work so that we cannot be attacked also, to prevent other people from attacking our work. And also this will also help us to appreciate that the work can be attacked. And so in so doing, we can then come up with means of preventing that. Now, so that is cryptanalysis, and that is, we're saying that you want to access somebody's work without the keys, so you have to use other means. Now, for the RSA, there are many ways of attacking it, but some of them are very difficult. And even the one which is, which I'll be talking about, is also very difficult if you have to use as a bigger prime number. If you have to use a bigger prime number to avoid somebody guessing the prime numbers you used, then it becomes very hard. You see, we had this public key M, and then we had the Q, the phi of M. Then we had P and Q. These were secret. So this was secret, and also D was secret. This D was the key that would be used for decrypting. Then we had E, which was public. So what was public is M and E. M and E are public. P, Q, and D, we said they should be private. And we also said this one, phi of M, should also be private. Now, for you to attack RSA, you must be able to factorize, to write M as a product of its prime factors. And you see, there are only two prime factors here, and we've chosen them large enough. And what you discover is, if it's a very large number, it's not easy for this person to factorize it. And so that is why we choose them very large. Now, for this person to factorize, if he has a very powerful computer that can factorize, and then he can do that. He can attack it if the computer can do it. But computers which are currently in existence, if you chose a very large M, it might take years to factorize this M. So for the RSA to be attacked, M has to be factorized. And that is why he said that this phi of M should be kept secret. Because if somebody has phi of M, you know phi of M is just P minus 1 multiplied by Q minus 1. So if somebody knows this, then this person will just solve a quadratic equation, because this phi of M, when you multiply this will give you PQ, and then you have, what you have is P minus 1, and then Q minus 1. When you multiply, you have PQ, then you have minus P, and then you have minus Q, and then you have plus 1. Now, so somebody can work out can work out this and find what if this one is known. If this one is known, it's easier to calculate and come up with by just factorizing. You see, this one can, by working out this equation, you can solve for P and Q if this number is known. If phi of M is known, you can solve for P and you can also solve for Q. That is why this must be kept private. Now, so that means for RSA to be attacked, then it's either M is a small number, the prime numbers you chose was smaller numbers, so that this person can even use guesswork. You can try, you can say, let me try P as let me assume that P is 3 and Q, I must assume, is 5. So you can try, you can keep on trying, and that is what we call brute force. Brute force method, where you are trying every option. You are trying, and if there were very small numbers, you realize that very few attempts would give this person the P and Q. And once this person has P and Q, then this person can read all your communication. Now, so I want us to look at the first method of attacking. I've already mentioned it, the factorization attack. And that one I've said that supposing that Eva is the person who is supposed to attack this, there are two ways. If Eva can factorize this number, into the prime numbers P and Q, then Eva can calculate phi of M by just using this equation. Yeah, if she can factorize this, then she can calculate this. And once she gets this, Eva can now, because E is public, and she has managed to factorize, and that means she can now calculate phi of M. That means once she gets phi of M, she can now calculate the decrypting key. She can calculate the decrypting key, which is D, and D, we said, is just the inverse of E mod phi of M. That is why now she was looking for phi of M. Once she gets this phi of M, she can use it to get D, because E is known. E is in the public domain. It is known. So the only thing she's targeting, can I get phi of M? Once she has phi of M, she knows that E multiplied by D is congruent to 1 mod phi of M. So once she gets this phi of M, she can use the extended Euclid's algorithm, because she already has an E. She knows what E is. She can get what D is. And once she gets D, it means every message you bring, she'll be able to, if she gets that message, she'll be able to decrypt it. This is what we call the factorization attack. Factorization attack is where the intruder attacks your M, which is in the public domain, and tries to factorize it. That should be the intruder will be trying to factorize by use of a computer. So maybe an algorithm of factorizing, and there are several of them. There are several algorithms, but none of the known algorithms can factorize a bigger M. I've said that for M should be chosen to prevent this factorization attack. To prevent this attack, M should be chosen to be 1024 bits long. So that should be a very big number. And so that means if you are to use the modern computer, it will take ages to factorize that m. If it's this long, it will not be easily factorized. Now, so the other thing I've said, this should be kept constant, should be kept secret. Because once the person gets this, can also use it to get these two. And now you realize why these two are kept secret. These two are kept secret because we don't want our intruder to know what phi of m is. If the intruder gets to know what phi of m is, since the intruder already has E, this intruder will be able to get D. And therefore, he'll be able to decrypt our message. So that is why P and Q were kept secret. So I've again explained why this must be kept secret. And that is just to help that our intruder does not decrypt our messages and read or our communication. Now, so that is one type of attack on RSA. I've already said there's another one, which we call the brute force. Brute force, that one is very hard for anybody to use it and attack the RSA, although it's a method, but it's a very hard method for anybody to use because what this method does is that you're trying every possibility. You're trying every possibility. So you have the ciphertext. You've been brought the ciphertext, and you know that the decrypting key is supposed to be a member of, it's supposed to be the inverse of E, supposed to be the inverse of E mod phi of M. So what that means, what this means, I know what phi of M is. I know what phi of M is. These are elements which are relatively prime to M, relatively prime to M. Now, supposing I have this group, because these are elements of a group, supposing I have this group, and this group has these elements which are relatively prime to M. One, supposing M is, let me say M is 7. Let me use 7. Let me use 7. So if M is 7, I know the elements here are 1, 2, 3, 4, all the way up to 6. These are the elements here. So E was chosen from this. E is one of these. Once I choose E as one of these, then D is the inverse of E. D will also be one of these. D will be one of these elements. So I know what M is. So supposing M is 7, and let me assume that the person who wrote the message used a very smaller M. If M is 7, I'm trying all these elements to find what is the inverse of E. I'm trying all these elements. D was, you see, I want to see, once I get the ciphertext, I want the ciphertext raised to D. So I try my ciphertext raised to 2, for example, then try to read it and see whether it makes meaning. If it doesn't make meaning, I leave it. I try 3. C raised to 3. And look at it and see whether it makes meaning. If it doesn't make meaning, I leave it. I try until you try all of them. One of them will make meaning. So that is what we call the brute force method. But now, if M is too huge, it means this person has so many numbers to try. And so the person will give up. Will give up along the way. He may not want to try all the numbers. from, let me say, from, you see, you can use a prime number which is one page, a number which is one page full. So let me say a number like 3, 8, so that this number is too long until it covers the whole page. So this person will not try all the numbers, try 1, try 2, try 3, and so on. So brute force method is impossible. Nobody can use it to decrypt communication done by RSA. So the only method that people can use is this factorization attack, but this one requires that somebody has a very powerful computer to try and factorize. And again, I said, if the number is too huge, even the most modern computer may take ages. Now, the other method of attacking is what we call the chosen ciphertext attack. This chosen ciphertext attack, how it works is that, supposing I was to send a message to somebody, and let me say my message was P, and then I create a ciphertext out of that and send to the person I want to send. So the intruder who is in the middle gets this ciphertext. And once he gets this ciphertext, this intruder multiplies the ciphertext by a certain number. Now, you see, I was sending the ciphertext, let me say to Alex. It has not reached Alex. The intruder has gotten it. The intruder changes this message. And then after changing this message, now sends the message to Alex. So if Alex gets the message now from the intruder, not from me, and the intruder has a way of making people think, when he communicates, people think that it's me communicating. So, and he has gotten hold of this ciphertext. He manipulates it, multiplies it with another number, and then sends to Alex. So Alex thinks it's me who sent the message, decrypts the message, and sends by some other way to this intruder, supposing the intruder now gets the decrypted message from Alex. Now, you see, what the intruder did, he took my ciphertext, multiplied by a number, let me say even 2, just giving an example. Then takes this new message, now the new ciphertext that he forwards to Alex. Alex gets this and decrypts, then sends it back to, he may not even send it back, but maybe the intruder has a way of getting this file, the decrypted message. Once this intruder gets this decrypted message, it can now use that to calculate and get the original message that I wanted to send to Alex. Let me just show you how it works, and maybe we'll look at an example. So, but briefly, that is what I've just explained. I've said that here, the attacker chooses the ciphertext messages and gets decryption assistance to obtain corresponding plain text. So how it works is that, supposing it's me, I encrypt a message. Let me say it's my message, my original message is P. I encrypt it using E. So this is my ciphertext, P raised to E. Now this is the message I want to send Alex. But before it reaches Alex, the intruder gets it. The intruder gets hold of it. And as I had already explained, the intruder changes this message and multiplies it by, let me say, X. So this is what I've said. So if is the intruder in this conversation, if gets my message, and then since Eve knows that we are using mod M, M is in the public domain. M is in the public, and everybody knows because it was a public key. Now, Eve knows that we are using this M. So he chooses one number which is relatively prime to M. Eve chooses one number which is relatively prime to M. Let's say she chooses this X. What she does is that the message I was sending to Alex, she multiplies it by X raised to E. Why is she multiplying by X raised to E? Because of this reason, she's also trying to encrypt. She's encrypting the X. Encrypts the X. She has just chosen X from one of the numbers which are relatively prime to M. Then she encrypts it. This one was already encrypted. I encrypted this one. I was sending it to Alex. So she now encrypts hers. After encrypting hers, she multiplies by X. Then sends this, the product, which I call Y. She sends it to Alex. Now Alex gets this Y and thinks it's me who has sent it. What he does, he decrypts the Y. He decrypts this Y. And he thinks it's me who sent the message. Now, it decrypts the Y. How do we decrypt? The same way we said to decrypt, you had this private key, was holding this private key. So he takes the message he has received, decrypts, raises it to that power, D. Let's say this is now the message Alex gets. And he thinks this is the message I sent, the plain text. Now, this is what the intruder wants. This is what the intruder wants. The intruder will look for a way of getting this message, this Z. So you see the intruder is just trying to behave as if he's the one who's sending the message. So maybe there's a way the intruder will work out to obtain this Z from Alex. Now, let's say the intruder gets it, is Z. Once the intruder gets the Z, goes back to the calculations, knows what Z was. Z is this. Z is Y raised to D. But what is Y? What is Y? So we go back and find out what Y is. Did Y come from me or from the intruder? We go back. Alex thought that Y had come from me, but Y was coming from the intruder. Y is C multiplied by X raised to E, but C is the one which was coming from me. E is the one which was coming from me, and it's P raised to E. So we just go back and substitute. Where there is Y, we substitute this. And then where there is C, we shall substitute P raised to E, because P raised to E is our C. So that's what we just want to substitute. So Alex had found Z by taking Y raised to D. So the intruder knows what Y is. The intruder knows that Y is C raised to C times X raised to E. So when you take this, just taking this part, that is Y. Y is C multiplied by X raised to E. Then now raised to that D. But what is C? Now you can first of all take inside the bracket, just take all of them inside the bracket, this power. So it will be C raised to D times X raised to E multiplied by D. But we know that E is the inverse of D. So that means E times D gives us 1. So this part then gives us C raised to D multiplied by X. The intruder knows what X, the intruder is the one who chose the X. But now what is this? What is C raised to D? C raised to D is P. Just a minute. Yeah, so C, what is C? Just going back. C is the ciphertext I had sent. C is P raised to E. So that means C raised to D, C alone is P raised to E, then raised to D. That's what you get. Then multiply by X. E times D is 1 because they are inverses of each other. What you get is P raised to X. And this is the same as Z. So you now have P. In fact, to get P, you just need to make it the subject of the formula by dividing both sides by X. And since this is modular arithmetics, we don't multiply by the inverse. What we do, we just use extended Euclid's algorithm and find what P is by using, because this is the same as Px is Z mod M. So you know you have P, you have X. The intruder has an X. Is the one who chose. He knows whether it's 7 or 4 or 3. Just wants to get what P is. So P is the unknown. P is the unknown. So the intruder solves for P by using the extended Euclidean algorithm. So that is how this attack works. So the attack works. The intruder plays with the two people that are conversing. Once the message comes, the intruder gets it and then multiplies it by another number and sends it to the recipient who was supposed to get it. So the recipient unknowingly decrypts this message. And maybe after decrypting, this person is not very much strict with his information. In some way, the intruder gets to know the Z that he got after decrypting. Once he gets that Z that the guy decrypted, then this guy just comes and works out this way to obtain P. So he knows that Z has been obtained by taking Y raising to D. But the intruder is the one who came up with Y. The intruder said Y is C times X raised to E. So now this one is substitutes there. So that means Z now becomes, instead of Y, we have C multiplied by X raised to E, then raised to D. And so this is same as C raised to D, and then X raised to E times D. But E times D is 1. So this gives us C raised to D, and then X. And now the intruder knows that the message, the ciphertext C is P raised to E. Now substitutes here, and you have P raised to E, then raised to D times X, which is the same as Px. So Z is Px. And he has obtained the X from the guy who got the message. uses the Euclidean algorithm and finds P. So that is how this method works. So that means if the recipient of the message is very keen and hides this Z after decrypting, if the Z is not gotten hold of by the intruder will be unable to proceed. But once the intruder gets this Z, is able to proceed and get P. Now we can get the original message that I intended Alex to read. Now we can look what we can read other methods of decrypting, but what you're saying is it's not very easy to break the RSA if the prime numbers were chosen properly, and if what is supposed to be secret was kept secret, and only what was meant to be public is left to be public. Now, one of the applications of the RSA is the digital signature, and this is very important. We shall go through it, the digital signature. So we want to suppose that somebody wants to get some, let me say, contract with an insurance company. You see, if I was to get a contract from an insurance company, and maybe I have a broker, the first thing you do, maybe you call the broker. And the broker gets the contract, and then sends to you. Now, there are various ways of sending this contract. The broker may decide to have this contract in a hard copy, signed, then sent to you by maybe a courier or any other means. So the contract comes to you, and then you sign and send it back. The other way is that this broker may want to send somebody just for hand delivery. So it's delivered to your door, you take it, sign it, and then it's taken back to the broker. So the broker is thinking of what way is secure. So for instance, if I was to bring it, supposing I'm the broker and I bring it myself and you sign, I'm sure it's you signed. I'm sure it's you signed. But if I was to send somebody that I trust, again, I'd be sure it's you signed, because if I trust this person, I'd be sure that it's you signed. But that is a process that will take long. Even sending a courier might take long. Maybe it's delivered to you, you sign, again, take some time, post it back. So it takes long, and again, it's slightly. So it might take long and slightly expensive. Now, the broker may also decide for a method that is faster and one that is less expensive. And maybe that one is by just sending you an email with a contract to sign. So does the contract and then sends it to you by email. Now, so the problem is, if it comes to you by email, you may sign, but how will the broker be sure that it's you signed? Because somebody else might sign it for you. Somebody else maybe in your household might sign it for you, or an intruder along the way may sign it and send it back to the broker. So that is now when RSA now comes in to ensure that contracts signed are then, if they are signed, you sign, supposing it was Linet who was signing, then the insurance company, if the RSA was used, the insurance company is sure that indeed it's Lynette who signed. But if it was to be via email, it's not very easy for the insurance company to tell. So that is the story I've written here. If I just got the digital signature, this is story. I will just say, let us suppose Lynette applies for insurance. She calls up her broker, Ken. They negotiate, and Ken sends her a printed contract in an envelope via mail. Lynette will sign after reading and then mail it back to Ken. However, this process would take long and is a bit expensive. So Ken has also another option. The option is to send the contract via email. And when it reaches Lynette, she signs and then approves it. That will save time and money. But there's only one problem. There's only one problem. You see, this broker did not encrypt the message. So the broker believes that it's Lynette who will sign it. But maybe somebody along the way gets the message or the contract and signs it back. The broker is not in a position to tell if the person who signed is Lynette. So the only way to guarantee that it's Lynette who signs that contract. So when you get it as the broker, you are sure that the person who signed this is Lynette, is now the RSA technique that we are supposed to learn. This is one of the techniques of signing these digital signatures. There are others. There are others, and we shall look at them. Now, how does it work? Just works the same way we did with the RSA algorithm. For instance, we want to call this contract. Let's call the contract N. That message in the contract, let's call it N. And let's say it's Ken who has written this. Ken has written this contract and we're calling it N. So before Ken sends this message to Lynette, what we said earlier, the recipient of the message has to choose the prime numbers. So the recipient of the contract is Lynette. Lynette chooses the prime numbers P and Q. And we said they should not be equal. So this is just the same RSA algorithm. Because Ken is the one to send the message, but before Ken sends this message or this contract, Lynette has to choose the prime numbers that she is supposed to now keep secret, P and Q. And after choosing that, we said she then gets their product, call it M. And remember, as we did for the RSA algorithm, M will be a public key. P and Q will be private. After getting M, this product, and after you will then use the P and Q to find phi of M, just as we did. That is the same Lynette doing, finds phi of M. And this is the formula, P minus 1 times Q minus 1. Then Lynette goes further and it chooses an integer that is relatively prime to phi of M. An integer that is relatively prime to phi of M. And again, choosing this integer, it's advisable that it should be a very large number also. It should be a very large number also. So that somebody cannot easily get its inverse. Now, so E is a public key. So after Lynette has done that, she has to publicize the public key, which is M and E. Remember, this is what the broker will be using. to encrypt. And remember the D, she has to calculate the D, and the D we said is supposed to decrypt. But let's see what she does after getting this, choosing E. She computes D. D is the inverse of E. She computes it, then makes these two public and keeps the private ones. She keeps the private ones. She has been sent, she has been sent this contract. The contract was not encrypted. It was just sent. It's just a letter. And we call it N. And you know, if it's a letter, it has the sentences, of course. You know, for you to decrypt and encrypt, you have to convert to numbers. Now she reads the contract. The contract was sent without any encryption. After reading the contract, she puts her signature. This is the signature. Take N, and N was the contract. So supposing the contract was sentences, we've said we've converted these sentences to numbers. And after converting these sentences to numbers, now raise it to D. Remember, D, we always use it as the decrypting key. But in the signatures, the digital signatures, we're not using it as to decrypt, because nothing has been encrypted. Nothing has been encrypted. So we just take N, raise it to D. And after N is raised to D, Lynette has now put the signature. That is now the signature. Lynette sends to Ken, the broker, N and S. N and S. N had come from the broker. S is the signature. So what you are saying is, Lynette is sending a signed document to Ken. He's sending N and S. N had come from Ken. S is the signature that she has appended. So she's sending a signed document. So this is what she sends to Ken. So Ken is now to verify. You see, what Ken was supposed to do, the broker is just supposed to verify, is this signature really coming from Lynette? Because it could be somebody else signing the contract for Lynette, and that is not good. Because maybe the person may even reject the contract and pretend that it's a Lynette who rejected. Or the person may accept the contract with the very wrong terms, and you think that it's Lynette who accepted that contract. But now you, as the employer, you need to verify whether it's Lynette. Now, how do you verify? Lynette has sent to you this document, which is signed. So for you to verify, you go to the Lynette's public key. You go to Lynette's public key, get E. After getting this E, raise it to this. This is what Lynette had sent to you. Lynette has sent you S. Raise E to S and see whether you get the original message you sent to Lynette. You just want to see whether you can get the original message you had sent to Lynette. So you take the message Lynette has sent to you, which is S, raise it to E, which is in the public domain. What do you get? You get N raised to DE. You get N raised to DE. But remember, DE, they are inverses of each other. So D times E is 1. So that gives you n raised to 1, which is n. So if you can get n, and n is the message you had sent to Lynette, then you are sure that it's Lynette who signed this document. Because this key only comes from Lynette. This public key comes from Lynette, and the D, only Lynette knows it. Only Lynette knows the D. Nobody else knows the D. So she just took your message, raised it to D. Now, when you get this message from Lynette, raise it to E, and you see whether it gives you back your N. See whether it gives you back your N. So if it gives you back your N, then you are sure that it's Lynette. Any question up to that point? Yes, you can still hear me. Is that okay?
Yes.
It's okay. Thank you. Now, that is how to do public and digital signature by use of RSA. And as I said, we have several other ways of digital signature, doing digital signature. And it's just a way of trying to verify that the documents that have been signed, they indeed have been signed by the people alleged to have signed them. So you know, when Lynette signs it, there is no way she can deny that she's the one who signed it, because only her knows the secret key, which is D. Only her knows. So for you, just take the message she sends to you, and you see she had already raised it to E, not to D. She had already raised it to D. So you only need to raise it to E. And you know, it's how calculated that D was the inverse of E. So it means you just raise it. You'll get a very big number here. Get a very big number and use the fast powering algorithm. Reduce this and see whether you get N by use of fast powering. And because when you multiply these two and you're just using a calculator, if you're using a calculator, it'll give you a very big number. But remember, this is mod M. Mod M. To give a big number, mod M. Then work on it using the fast powering algorithm. You can even work on it using other methods like the Euler-Phi theorem and see whether you get N. Once you get N, you are sure it's Lynette because only Lynette knows D. So she cannot deny this signature. If she denies, she has to tell us who else knows what D is, because this is a private key. It's a private key. Now, I want you to try these questions. I didn't give you these questions earlier, but I want you to try them. I hope you've not forgotten the concepts. Like this is question one. Question one says, for each of the following, encrypt the message M using RSA with the modulus this and the exponent E to obtain the ciphertext. Then find a decryption exponent D and verify that C raised to D is M. Now, just to remind you what we are doing here. P has already been chosen for you. Q has already been chosen for you. And so this person already did E for you. Remember what we normally do is that somebody chooses P. I've chosen smaller ones for purposes of calculation. So P times Q gives us our M. M has been given as a message. M is a message that we're supposed to, this is our plain text. So let's say it gives us N. Gives us N. And this is not, so what is this? So this will be 65. 65. Now the other thing you're supposed to get now is phi of M, because the question is find D. How do you find D? You require phi of M. Phi of M is 5 minus 1 multiplied by 13 minus 1, which is 4. 4 times 12, which is 48. Now you find D. How do you find D? Remember, D times E is congruent to 1 mod phi of M. In other words, E has been chosen for us, so it's 7. D is congruent to 1 mod phi of M. Phi of M is 48. So find D. To find D here, you'll use either the extended Euclid's algorithm, or you'll use the Euler-Phi theorem. You find D. That is the first question. Find D. After finding D, you've been told, now verify. Oh, we've not encrypted. We've not encrypted. The question says what? Using the RSA with the modular Z and exponent to obtain the ciphertext. So we need to get the ciphertext. But you've already gotten the D here. Now the ciphertext, how do you get ciphertext? We have our message. We have our message 6. Raise 6 to E. Our E is 7. Mod N 65. Mod 65. So 6 raised to 7 mod 65. Get what that is. So this is our ciphertext. After getting ciphertext, you come and decrypt. So decrypting is now this ciphertext raised to D, the D we've obtained here. The D that you obtained here, raise it to C mod 65. This is what they say, verify. Verify, it gives you 7. It gives you M. Our M is 6. So you just want to verify that this gives you 6. As the question is asking. Question is asking that now. And it's the same thing here. Question 2. Alice chooses the 2 prime numbers, and she also chooses this E. What public modulus does she publish? What is her decryption exponent? Now, so what is a public key? What is a public key? That's what is the question here. What is M? What is M? M is a product of these 2. So she will publish that. That's what the question, the first part is asking. What is M? Now, what is her decryption exponent? The inverse of 71. So to get the decryption exponent, you take 71. D is congruent to 1 mod phi of M. What is phi of M? Phi of M is 113 minus 1 multiplied by 167 minus 1. This is phi of M. So that's how you do that question. Now, there's one that I want us to look what is the one I'm looking for. Now, this one, nothing new. It's the same thing. Alex chooses 7 and 11 as a private prime numbers, calculates n, and then calculates phi of m. If he chooses this to be public key, calculate d. It's the same as we've done above. Now imagine that when Jill wants to send a plain text of 15, show how she would encrypt 15. So that's the same thing. That is not the question I wanted to look at. But this one you can try. Even this question 4, you can try the same concept. The one I wanted us to slightly look at is number 6. What about this number 5? Number 5 says, you have been sent the following message. You may use your computer to encrypt. No, it has been encrypted. This is a message. This is the encrypted message that we've been sent. And we are told she has been encrypted. It has been encrypted using P and Q are this, M is this, and E is this. Decrypt the message. This one I put it here so that you can use your computer. You can use your computer to do these calculations. You see, for you to decrypt this message, first of all, you get the inverse of E. Just a minute. Now you have this E, so you have to get D, the decrypting key. So what do you do to get that? You have E, you want D is congruent to 1 mod phi of M. Phi of M. How do you get phi of M? Since P and Q are prime numbers, it's easy. Phi of M will just be given by 312 times 372. So that is phi of M. Now this will be a very big number. This will be a very big number. And then this is also a big number. So I was trying to come up with a slightly bigger number so that you can use your computer also to try and work out this. Now you also use your computer, for instance, you have this, after you found your D, you see this is the ciphertext. This is the ciphertext. So after you get the D, you raise D to each of these blocks, raise D. And we say that we are decrypting each of them, decrypt each of them. You find that this D might be a very big number. So it's a very big number. Supposing it's a very big number, then do this mod M. Our M is this. Our M is 1,16749. Do this one also. Raise it to D, mod M. This one raise to D, mod M. Raise to D, mod M. So that is what we say, you're decrypting the message. So I try to come up with this bigger number so that you can also come up with an algorithm to do this. Now look at this, encrypt this, encrypt this. So this is the message. And you've been told use P to be 5 and Q to be 17. This one I tried to choose the smaller numbers. But how do you encrypt this? Just as we did earlier, convert this to the corresponding integers. I use the alphabet. Using the alphabet, of course, A is 0. So this will be 0, 0, 0, 0. What about Y? Y is 24. I think it's the 24th alphabet. Is it 24th or? Yes. You see, what we do is this. Let me see. What we do is this. A is 0, 0. B is 0, 1. So C will be 0, 2. D will be 0, 3, and so on. This means Z will be 25. And Y will be 24. Yes. Now, so convert all this, you convert all this to their respective integers. And then you look what phi of, now you look at M, you look at M. That number should be less than M, should be less than M minus 1. So you may find a very big number. So when you find a very big number, as we did in a previous example, you break into blocks. You break those numbers into blocks that are less than M minus 1. Just like these blocks here, you see like these blocks. You break into those blocks. After breaking into those blocks, each of the blocks raise it to 3. Each of the blocks raise it to 3. Mod M. Raise it to 3, mod M. And then the answers you get are also in blocks. You send those blocks as they are, as the ciphertext. That will be the ciphertext you send as they are. When the recipient gets the ciphertext, this recipient will also decrypt the blocks independently. And then after decrypting, joins them. And then there'll be numbers, So now goes and finds out, what does this number mean in alphabet? Finds maybe it's a C, that one maybe is a D, the other one is a Z. Then comes up with the letter in alphabet. Now those consonants and the vowels, arranges them such that they form words, words that make meaning. Now, this question reminds me, I don't know whether you normally answer these questions where you're supposed to implement some program. So that, oh, there's one that somebody answered last time. It was, I think it was Renate. Supposed to, again, for this question, come up with a program, implement RSA. And I said, make your program as friendly as possible. In particular, the person encoding or encrypting a message should be able to type in their messages as words, including spaces and punctuation. Similarly, the one who will be decrypting should see the message appear as words with the spaces and punctuation. Now you try this and see. It's always good to try some of these, writing these programs. Now, so this is just, this is a question that we've just done before. We want signature. So the question is, the net has a public RSA modulus, this, and which is obtained by these two prime numbers. and she has chosen this E. She wants to sign the document, and the document is M7, which is 7. Now, what is the signed document? The signed document is supposed to be 7D. Because what is she supposed to do? She's supposed to take this 7 and raise to D. So that means for you to answer this question, find D. Find D. For you to answer this question, you must find D. Now show that Alex's calculation verifies that the document you produced in part A is valid. So just saying, show that this document was signed by Lynette. So what that means, take the message what you found here. Let me say that this is the signature. Take this signature and then raise it to, you have already calculated D. The D here you've calculated. Raise it to E, mod 119. See whether this is 7. See whether that is 7. If it is 7, it means you verified that this message for sure came from Lynette. So that is what you'll be doing. That is, of course, the notion of public signature by RSA. That is that notion. Now the last question, the same Lynette uses RSA signature. This time the modulus is that, and the public encryption exponent is this. This is our E encryption exponent. So this is our E. She sends 3 documents to Alex. This time, Alex is supposed to tell which of these 3 is forgery. Which of these 3 is, this 4 is forgery. She has sent how many documents? She sends 3, which are genuine, and 1, the 4th one, forgery. No, it's not Alex, it's not her. But who does that? She sends 3 documents to Alex with the signature attached, but Alex creates another one, decides to forge the 4th one for her. I changed the names. I think this is supposed to be Lynette. Now, which of the 4 documents is forgery? Now you see, there are times you can sign some contract with the company, and then a company wants to again forge another one for you. Maybe the MD maybe wants to forge. Are you able to tell which one is forgery? Which one has been forged? Using the RSA, we can do that. You know what we want? This is the message you was sent. You see, this is, what is this? This is the message that is coming from the company. And then this is our signature. So this is what we want to verify. We just want to verify that. Let me just show you this part. Let me just show you whether this part is forgery or correct. And then you show the rest. Just want to show you whether this first part here is forgery. Now, how do I show that? This is my E. I find D. I find D. So 7D should be congruent to 1 mod 5 of M. 555. Now find what D is. Find what D is, and this, what is 555? 555, 55, let me just see. 55, 5 goes there, 11, then goes there 1. So in fact, 555, these are two prime numbers. 555 is just, in this case, it's easy. It is 4 times 10, which is 40. Because it's just 5 times 4, 5 times 11. 5 minus 1 times 11 minus 1, which is 40. So 7D is congruent to 1 mod 40. Now, we want to find D. We are using the extended Euclid's algorithm. We are saying 40, 7 goes there. How many times? 7 goes there 5 times. 5 times. Because of that 5, yes. And the remainder is 5. And then 5 into 7 will be 1. And the remainder will be 2. And then 2 into 5. 2 into 5 will be 2. And the remainder will be 1. Then 1 into 2 will be 2. And the remainder will be 0. So 1 is the GCD. Now reverse. When you reverse, what do you get? When you reverse, you have 1 is equals to 5 minus 2 multiplied by 2, which is same as 5 minus 2 multiplied by, instead of 2, we write the equivalent. Write the equivalent, which is 7 minus 1.4 multiplied by 5. And so this is the same as 5 minus 2 multiplied by 7 plus 2 multiplied by 5. Yes, I hope that is okay there. Let me just look at it again. 2 multiplied by 7, yes. 2 multiplied by 5. So this is the same as 5, not 5. It's minus 2 multiplied by 7. And this 5 and that 5 are like terms. So this is 3 multiplied by 5. You just go through and look at the steps again. Now let's now substitute the 5 by the equivalent. Substitute by 5 by the equivalent. This is negative 2 multiplied by 7 plus 3. Instead of 5, you have 40 minus 5 multiplied by 7. Yes. Okay, let's open that bracket. I want to do it from above here. I want to do it from here. This will be negative 2 multiplied by 7. Open that bracket. I have 3 multiplied by 40. 3 multiplied by 40. And then this one I have negative 15 multiplied by 7. Negative 15 multiplied by 7. So what does this give me? This is 3 multiplied by 40. And this negative 2, and that is negative 15. That gives me negative 17 multiplied by 7. And this is, it was equal to 1. It was equal to 1. And of course, that is what we wanted to get. We wanted to get a number which, when multiplied by 7, gives me 1. That number is negative 17. So in other words, the inverse of 7 is negative 17 mod what? Mod 40. What is negative 17 mod 40? Just add negative 17 plus 40. That gives you 23. That means the inverse of 7 is 23. This is our D. This is our D. So what we now want, you know what we did? What happened when Net receives this message? What message did she receive? She received 3. She received 3. When she receives 3, 3 had been raised to. 3 had been so the original message. Okay. She receives 3. After receiving 3, she raises to D. After so this is our signature. Now, so let's now raise 3 to D. We've just found that D is 7, no 23. We found that D is 23. Let's raise 3 to 23. And this is mod M. M is 55. Now this one you do it with your calculator. You can do it with fast powering algorithm and see what that one is. Now after raising that, how do you verify? What you verify is raise what you get. Raise this answer. Raise it to E. Raise it to E7. After you worked out, raise it to 7. And see whether you get the number here. See whether you get the number which is here. If you get the number which is there, then it means it's correct. And you can do it for all of them. You'll find that there is one, you see, following the same procedure. But for this case, E is 7. So once you get 23, 23 will be applicable to all of them. So just raise this one to 23. The answer you get, raise it to 7 and see whether you get what you have there. See what you get, what is there. Now maybe you can try that, and then when you meet next time, you tell me whether you succeeded. And if you did not succeed, maybe we look at it again. So let's try begin from there when we meet next time. Next time is even tomorrow. So maybe you can try it and we see. We can begin from there tomorrow before we go to something else. But we only begin from there if you tell me maybe you had a problem with that, or maybe you succeeded and you want to show us how you did it. Thank you.
Thank you, Doctor. I think we also look forward to the physical class where we do most of these exercises as well, and we get advice on past material. So those who are here, make sure you come to the Thursday session as well. See you tomorrow.